So welcome everyone, welcome back. So on today's lecture we are going to see more about some tools we have on the C++ STL library. So whenever you see STL, so this means the standard template library. So that's basically the name, and it's one of the core components of the C++ language. So this is a library that has been maintained forever since the beginning of the C++ language. And we are going to see today how we can take advantage of it, right? So in previous lecture we saw how to write our own functions, and then from this lecture on we are going to see how to use functions that are written on the STL library, as well as the containers. So I guess that on today's lecture we are going to see like more than half of the slides are with code, so that was the idea. So this is lecture number 4, but it's the 5th lesson on the course, and we have 10, so we are right in the middle of the course. So thank you everyone for joining the course so far, and I hope you're more or less enjoying C++. Okay, let's start. So the first thing we're going to see is C++ containers. Basically, what is a container is what you see on the screen is something where you can put data on. And as usual, so this is something that I guess that I say on all lectures, but the C++ world is usually divided in two. So we have the static world and the dynamic world. So whatever is static, this means that it should happen at compile time. So before you run your program, this should be already solved by you or the compiler, usually the compiler. And dynamic, whatever is dynamic, means that it's something that will happen when your program is running. So as well, we have static containers and dynamic containers. This basically, a static container is a container that is this. So its size is defined at compile time and cannot be changed across the execution of the program, and dynamic means that you can increase the size of this container. So the first victim of the day is going to be std array. So this is basically an array of data, and there's a really small example here. I will just highlight some details. So first of all, so in order to use array, we need to include the array header file, and this is how we declare an array that is called data, right? So we will need to pass two arguments, template arguments. So we will see how to work more with this on the last lesson on this course, but basically the first one is going to be the type of the array, and it's unique, so you cannot like have bananas in here and floating points, so or bananas or floating points. And then the second important thing is the size of the array. So this is a number, and it should be defined at compile time. So this means that you cannot, for example, ask the user for input and then define the array according to this input, because this is something that will be happening at runtime. So at compile time, you need to say this array is of size 3. Good. Then in this case, we are just printing the elements of the array, that is 10, 100, and 1000, and then we're going to use some member functions of the array, and this is something that you will start seeing and using from now on. And these functions, so there's just two examples. One is empty, that this will give you a boolean, and then this will tell you if the array is empty or not, and then the size member function will give you the size of the array, right? So this is actually easy to use and hard to misuse. So as a recap for arrays, so you need to include this header file in order to use it. Then you will store a collection of items of always the same type. So remember, don't mix the type. I mean, you will get compilation error, so it's not really unsafe. So you will not be able to do it. And then this is how you create an array from data, and how you with the square bracket operator. So this is as any other programming languages. The indexing start with 0. So please, MATLAB friends, remember that on real programming languages, we always start indices from 0. So I see a lot of errors on homeworks usually and the projects because people are used to start with 1. So keep this in mind, it's always like this, except for MATLAB. There are some member functions like how to query the size of the array and some useful aliases. So that's the static container by default, but then what happens if you don't know at compile time the size of your container? So then you will be using STVector. So vector is basically the same as an array, but the difference is that you don't need to know the size of the container at compile time. So in this case, when you declare the vector, the only template argument you need is the type of the container. As well, this is unique. But then in this case, you will have a container of size 3, and then it's the same with the names container, but you can actually increase the size of the container. So one way of doing this, of many out there, is using inplaceback. So on this names array, you will inplace a new name that is called Roberto. And then that's basically how you create a new element. So this is something that you cannot do with arrays, because array is fixed size, a fixed size container. So if you say it's 3, so you only have 3 elements. In this case, you say I have a names container, and then you can put as many as you want. Actually, as many as your memory allow you to do. But let's pretend that it's infinite amount of memory. So this is vector. Analogously, to use vector, you need to include the vector header file. So this is implemented as a dynamic table, and then the access store items. You can do it just in an array with the square bracket operator. If you want to remove, for example, all the elements, just call clear function. And then basically you have 2 ways of adding new elements to the container. One is inplaceback, that this is the preferred way of doing it. This is something that started to be on the C++ 11 standard. And if not, you can also use pushback. That is historically the most used one, but nowadays you should use inplaceback instead of pushback, right? And then the take-home message is use it. So it's fast and flexible. And this should be your default container for any sort of collections of items of the same type, right? So in our field, arrays are great, whatever, but usually you will be handling and working with data that comes from a sensor, for example, and usually you don't always know like the size of the data of whatever. So vector is most widely used on our community than array. So just use vector whenever you need it. So there is only one drawback about vector, and it's that the fact that the size is unknown at compile time. The implementation of vector needs to do some operations even when you are using the vector. So there are some optimizations you can do in order to speed up your program. So the vector is unknown, but then they will define, so the C++ standard define a capacity, and then the size is not always the same number as the capacity. So the capacity of the vector is basically how much items you can store. So this is basically the amount of memory you will reserve before using the vector. So let's say you declare a vector and then it's an int, and then depending on the compiler and in the implementation, you can say, okay, I will just grab 100 elements of memory just in case. In this case, the size will be 0, but the capacity will be 100, right? And when you start adding elements to this vector, then this capacity will increase over time. And this is time consuming, right? So many pushback or inplaceback operations force vector to change its capacity many times, and this will slow down your program. So there is a function called reserve that will ensure that the vector has enough memory to store n items. So basically, if you know that your vector will be roughly 100 in elements, so we'll store 100 elements, then before adding any element, just reserve the amount of memory you actually need. And this way you avoid like reserving memory while your program is running. And this parameter n can be approximate, so if you don't know but you say, okay, roughly have 1,000 elements, you can just reserve 1,000 elements, and then if the size increase, then the capacity will increase as well. So it's not an array, so this can change at runtime. And this is a very important optimization. So if you start benchmarking using reserve and not using reserve, you will see that your program will speed up a lot. So here's an example on how to do this optimization. So we have a vector that is called vec. And then let's highlight some features. So whenever you declare the vector, so it's size 0 and capacity 0, and then in this case you're reserving 100 elements. So in this case the capacity will turn 100, and then you will emplace 100 elements on this vector. Whenever you reach this point, so if you print the size and the capacity, you will see that now the size is 100 because you added 100 elements, but capacity is still 100, right? And then let's pretend that we don't reserve memory. And then when you declare this element, so another vector, vector 2, the size is also 0 and the capacity is 0. But then you execute the same loop, and then when you inspect the element at the end, you will see that the size is 100 because again this is 100 elements on both loops, but the capacity is bigger. And actually there is some point in time where you reserve more memory than the one you need here, because you didn't tell how many elements you need on this vector. So at some point it will just start eating more memory just in case. So this is an example of how you can optimize this. So this is something that I will start hopefully doing starting from now. So now we have we are seeing more real C++ code. So I would try to search examples on real world libraries from our community and try to show you that people does use this. So in this case, so Open3D will be probably the most seen one on these vectors, because it's a library that's really well written in C++, so it's really good place to go and find and search for really good C++ examples for any kind. So in this case, we have a point cloud. So there is a type defined in the Open3D geometry library. And then inside this point cloud type, you will have like 3 vectors: the points, the normals, and the colors, right? And each vector has an eigenvector 3D this is basically X, Y, and Z coordinates. So you will have a container containing like n elements with X, Y, Z points, right? And also the normals and the colors for each point. So this is how you can actually use a vector in our field, right? So there is a question: what is better, vector? Okay, so I will not read it loud, but I mean, we can say that it's the same, but the first one you wrote is better, because in the other one you will basically do a copy operation. But I will say that this is not extremely important, but it's the same. Okay, so one of the questions you might ask now is like, why using C++ container? Like C programmers will say, I can do everything with arrays, for example, right? And you might be confused, like, why do you really need these containers? So I don't know, maybe you can write your own data types. Anyway, as usual, I will try to reply to this question that I ask myself with some small examples. Remember that you're encouraged to go and try these examples. So all the source code you're seeing, it compiles. Maybe you're missing some include headers because I need to shrink the slides, sorry, but you can try this on your place. So basically, we want to inspect the size of a container, right? And then remember that C++ is all about writing the intention of the program. And then if I read this, like this sentence over here, it's not really clear. I mean, experienced C programmers will detect automatically what is this about, and actually if they really know C, they will define a macro, an ugly macro, to do this. that is size off with all capital letters, but anyway, you don't really see the intent of the program here. You want to see the size of the container, and then you have size of data, and then you're dividing this number by the size of the first element. So there is an explanation for that. I will skip it, but basically this is how you will inspect the size of the container on a C-like array. But then on the C++ world, we have a much better way of doing it. That is just calling a member function that is called size, that we saw it on previous example. Basically, you just call the container, and then you just call the function for that specific container is called size. And then the intent of the program is completely clear. I want to know the size of this container, nothing else. Moving forward, how we check if the element is if a C array is empty. So there is no really standard way of checking it. So one thing you can do is like comparing, for example, if all the elements are like equals to null, so this means that there is no memory allocated in there for the array, and then you kind of like know if it's empty or not. But again, this is not really clear the intention of the program. Again, in C++, you can just use the empty function, member function for any container, and then you will see, so this will give you a Boolean variable saying it is empty or not. So it's really easy to use, hard to misuse. So how to access the last element? So actually there is a better way of doing this in C, but I skip it just to make it look even more ugly. So we have an array, right, in C, and then the size of this array is n. This n is defined somewhere in a huge C program, and I forgot, right? Well, in this case, you actually see the elements, but let's pretend that you don't see this declaration. And then you say, okay, the last element of this array is 3, because I think it's 3, right? And then you don't actually remember if this is 3, this is 2, 900. You don't really know. And actually, if you do this, it will compile and it will run. But the thing is, there is no third element here, so you will access garbage on memory, and this is a runtime error. In C++, we can just call the back function that will give you access to the last element of the array. So in this case, you don't really need to know how big is your container, because you just call the back function, and then it's really easy to read, and you express the intention of the program really clear. So I want to access the last element of this container. It's perfect. Array, vector, you name it. And then lastly, let's see how to clear an array in C. So one way of doing this is calling the memset function. That this is already a bit ugly because you're calling a third function, so it's not part of the array itself. And then if you read this, it's again, it's not really clear what you really want to do here, unless you're an experienced C programmer. But you're basically trying to clear this array. So if you print the array before and after, you will see Ignacio first and then nothing. But the thing is that depending on some variables, let's say, if you try to do this with floating points arrays, this might not work. So this is not even super safe. So in C++, what you will do is just call the clear function. So you have a container, you want to clear this container, then you call the clear function. It's really easy to use, hard to misuse, and the intention of the program is clear. And by the way, please don't do vector of char unless it's really necessary. So if you want a string, just use a string. So this is, I use these characters just as an example, but again, a string is sort of container, and you can actually call clear, size, empty, all these functions, right? So answering your question that you didn't ask of why using C++ container, so why not? I mean, they're the same speed as C style arrays, but much more safe, right? And improves a lot code readability and the usage. So when you write C++ code with containers, it's going to be much easier for you than just using C. And there's much more functionality built in within the array than in a C array. So you can call the size, empty, the front, the back, you can swap elements, and most important, you can use STL algorithms and much more. Anyway, so there's much more information. You can actually check the CPP reference documentation, link on the description on the link, and then you will see like how much you can do with these containers. Okay, so that was like all about arrays and vectors. Takeaway: don't use C-style arrays. So this is not allowed on your homeworks or your final project unless you have a really important reason that I doubt you will have. And then if in doubt, just use std vector instead of array or any other thing. Right, so these were containers that contain the same type of data. There's another kind of container. Actually, there are many of them, but we will see only two. On the C++ STL library, that is called associative containers. The idea of this is that you will associate data within the container. So one example is map. So the map container is a sort associative container. It contains key value pairs. So this means that for each key you must have a value. The keys must be unique, so you cannot like add two elements with the same key. And the keys will be stored using the less operator because it will be sorted, right? So whenever you insert a new element on the map, it will be sorted right away after you insert it. So your keys should be comparable, and this means that this less operator should be defined for your key type. The built-in types always work, so if you pick integer, float, or character as your key, this will work by default without doing any other work. And we will learn how to make your own types comparable probably in 2 lectures. So let's pretend that integer is not enough for your key, and then you need to define a new type. Then you will need to provide this functionality, and you will learn how to do it. And then the value can be any type, so you name it. It could be a pair of like integers and bananas, integers and string, integers and ducks, so you name it. It's whatever you want. And this type of associative containers, they're usually called dictionaries as well as in Python. So this is the equivalent to a dictionary in Python. How you create a container? So you will need to specify, not a container, like a map container. You will need to specify the key type. So for example, integer, and then the value. So this is any type, bananas, floating points, integer, you name it. And remember that key should be sortable. So you should be able to compare if one key is bigger than another one. You can check the size of the container with the size function. So you will start seeing a lot of these same functions across all C++ container. You can actually add a new item to the map using the inplace function. You can modify an item just using this syntax. So this is the same syntax as in Python, for example, and then many more. One thing that you can't still do is compare it with Python. Is like asking in a nice way if a key is contained in the map. So the way of doing this is like using the count function. So you have a key, for example 5, and then you want to check if this is on your dictionary or your map, and then you will need to call this function and compare if this is greater than 0. So this does not express the intent of the program really clear. And then the C++ committee already fixed this, but this is on C++ 20, that's still quite new. And then there's this new function called contains. So this is the same as when you in Python say like if key in dictionary. In this case, you will say if m contains key, then blah blah blah. So this will express the intention of the program better. Simple, really simple example. We will go through it really fast. So one thing you can like, I always recommend whenever using associative containers. So the type of these containers will be really verbose. So it will be like long types and ugly. So you can use the using statement to say, okay, I will use this student list type as an alias to this map of integer and string. So remember, this is the key and this is the value, right? So I will create this container. It's called CPP students, and then I will insert data on this container. So first I will insert like my ID, for example, and then my name, and then I will do the same for 2 other students. But the thing is, map is a sort container. So whenever you reach this point on the program, this will be the order of your container. So Nacho will be the first one, Pepe will be 0, and Marcelo will be 2, right? So if you print this information, you will see this order of the container because it's being ordered according to the key, right? So keep this in mind. So map is for order, for getting an associative container with order. There's another, like, probably more popular associative container that is an ordered map, that, as you might guess from the name, is the same as map, but the difference is that the key, so you will not be sorting your map according to the key. So it's the same as a map. The only difference is that the key type must be hashable, so you need to be able to extract a hash from the key, and then the typical usage is using with integer or string as key, right? The interface is the same as map, and it's faster to use than the map, and the reason of this is that whenever you insert a new element on a map, then you will need to sort your container. Of course, this is really optimized on the C++ STL library, but still you need to do work. And whenever you insert an ordered map, so keeping it simple, you're not doing anything more than inserting a new element. So it's a bit faster. This is the same example that we saw before, but the only difference is the type. So again, actually using this student list trick with the type alias, you don't need to change any of the code. So the only thing you change is this. And then instead of using map, you will be using another map. And then if you in place these elements, so this will be the first one, the second one, and the third one. Whenever you access this container, you'll see that the order of accessing this particular example is going to be on this increasing order. So Marcelo will be the first one, then Pepe, and then Nacho. So same code. Remember, it's better if you try it on your computer. The only drawback of this is that this key type, that in this case is we pick integer, must be hashable. This means that you should be able to provide a hash for this type. So in this case, whenever you insert this key, you will get a hash for this key, and then you will actually insert it with this hash on the container. But then the good news is that most of the built-in types have already defined this hash function. So if you use any of these types as your key for the unordered map, then you don't need to do any extra work. So integer, short, long, float, double, whatever, you can actually use it as a key on an ordered map. The way of iterating over these maps, so this is something we saw on previous lecture as a spoiler. So usually you will do like, you will iterate over the container. So this is a map, for example, and then you will use a key value variable, and then in order to access the key, you need to access the first element of this value, and in order to access the value, you will need to access the second element of this value, because that's the pair. Like the key is the first and the value is the second one. There's nothing wrong with this, but it's more code you need to write. And then starting on C++ 17, you can use this syntax and then just say, okay, for key value in dictionary, just use key and value. So this is much better to read, right? And then as a recap for maps, every stored element is a pair, so it must always contain a key and a value. the map has the keys sort, and then the unordered map, that is the most common or most widely used, has key in random order. So you don't know the real order of your map. And again, as an example, again, Open3D people. So if you inspect the voxel grid implementation for Open3D, you will see that the voxels, so in this case, so this is a voxel grid. So as an example, this, for example, this cube right here is a voxel. A voxel grid is the same type of data as an image. The difference is that it's in 3D. So if you see the voxel grid from one perspective, you will see basically an image. So, for example, this is the 0 coordinates for x. This is the 1, and then 2, and this will be the 0 coordinates for y, and this will be 1, and then 2, and then you have the z axis. So think this voxel grid as a 3D image sort of thing. And then how they did it, how they defined the voxels on the voxel grid implementation, they use an unordered map. So you can see that it's not something that I am the only geek out there using it. So the key for this map will be a vector of 3 integers. So this will be the key for the map, and this is basically the XYZ position of the voxel. Then the value for each pair will be voxel. So this is another extractor defined somewhere else, but for now, this red thing is one voxel. And then if you compare with the previous example, you see that there is something weird here. And this is basically the function to provide a hash for this vector of 3 integers. If you were using like integer or any other hashable type that is defined on the C++ library, then you don't need to provide this extra function. But in this case, this vector of x, y, z elements that are integers, there's no way of there's no standard way defined on the STL library of how to compute the hash for this. So you need to write your own function. And then you can actually go on the Open3D implementation and see how they did it. So there is a question that, can please repeat what do you mean by hashable? I will give you the most simple example. You have an integer, and then you will create a unique identification for this integer. So actually, hash itself is a huge topic in computer science. So if you go to the Wikipedia article, you will probably find a better explanation. But for some reason, let's pretend that you have one integer and then, or one type, and then you want to get a unique access code for this element. So that's the hash of the element. So if you write a C++ program and then you call std hash and then you provide the integer, you will see a really long number that is the hash for that particular integer. I hope that answers your question. But let's pretend that it's like a key for the element. In this case, for the vector of 3 integer elements, you need to provide a hash for each different element. So this is how you do it. And there's much more about containers, like much more. As usual, the recommendation, go to CPP reference and then check all the containers. So in this case, you see array vector. We only saw 4 containers, and there are at least 20 of them on the STL library. So make sure you check that out. And then, is there any other question about containers? Otherwise, we move forward. Okay, so let's quickly see C++ iterators. So taken from the C++ book, iterators are the glue that ties standard library algorithms to their data. Iterators are the mechanism used to minimize an algorithm's dependence on the data structure on which it operates. So this is one key concept. It's part of what is also called generic programming, and iterators are a really good way or mechanism to write generic functions or generic algorithms, right? So let's pretend you want to sort some sort of data. Then the best thing you can do actually is to write a sort function that works on any kind of data, not on vector of floats or vector of integers or array of string or whatever. So the idea is that with these iterators, you will be able to write functions that are strictly independent from the data structure on which you will operate. So by just inspecting the sort function, you will not be able to know to which data this sort function has been applied, right? We will see much more about, or not much more, we will see more about generics programming whenever we reach the templates on C++. But this is a way of doing generic stuff on C++ and it's using iterators. So this is a really key concept on C++. And then the STL library uses iterators to access data in containers. And then the iterators are similar to pointers. We will discuss this soon. And this allows you to quickly navigate through your containers, and most algorithms in STL use iterators instead of the data itself. And it's actually, most of the iterators are defined for all containers in STL. Once you have the iterator for any container, you can access the element that you're pointing with this iterator with the star operator. You don't really need to know much about this right now, but there's like a quick overview on the syntax, but it's basically the same syntax as a pointer. And then you can move to the next element using the increment or decrement operators. And then the idea is that you should be using range for loops as we saw on second lecture instead of using this. And you can actually compare iterators as it were any other thing. There is something that is called range access iterators. There is one type of iterators, and these are the most common used iterators, at least for containers in C++, that are defined for all STL containers. So if you're using any type of STL container, then you already have this iterator defined by default. So for example, begins, so this guy will give you an iterator, so whenever you call this function, it will return an iterator to the beginning of a container or array. Of course, this is, the intention of this is expressed on the name of the function. Then there is also cBegin, that is basically constant iterator to the beginning of the container. So you can access the container, but you cannot change its value. You can also access n and constant n, and then the r stands for reverse begin, and then constant r stands for constant reverse begin, and so on, right? So these range access iterators are defined in all these structures, so array, list, map, set, span, string, another map. So all those containers have these range access iterators, and there's one example. I will just skip it for now because it might be complex from the perspective of the syntax, so we should skip it. So that was all the information you need to know about iterators. And now, if you are ready, we will go through some algorithms. So let's actually go back to the first slide of iterators. So the key idea is that the iterators will be the glue that ties the standard library algorithms that we are about to see to the data where they operate, right? So it doesn't matter if we are using like a vector. So let's pretend that we are using a vector and then we want to sort. So we want to call the sort function. So we will not be calling a sort function from a vector type, right? So we will not pass the vector to the sort function. Instead, we will take another path that might be longer, but it's better in the long run. That is, instead of providing the vector, we will just provide the iterators, and these iterators will be fed into the sort function. And why we do this? It's because it's more generic. Because if we avoid like if we don't do this, then we need to provide a sort implementation for vector, and then so let's do it with arrows. So if we don't use iterators, we need to write a sort implementation for vector, one for map, one from list. Let's pretend that I have my own container, one for this guy. We are using Open3D containers, one for this guy. And then you need to actually overload this sort function for infinite amount of containers. So, and then let's pretend that you also want to, for example, do a find. So you want to find an element on the iterator, on the container, and then instead of using iterators, you will do one function for vector, one function for map, one for list, and so on. So you get the point, I guess. So a much better idea is to use the iterators as a sort of interface. So something like this. So this will be the interface between the algorithms and the data, right? So here you have data and here you have algorithms, right? And then you will write one unique sort function that will be operating with iterators. So with these iterators, you can access the elements of the container in a generic way. And then you will call this sort function, but instead of giving the data to the function, you will pass the iterators to this data. So you will say, this is how you iterate over my data. And then the algorithm itself will do its job without knowing which data it's using. So this way you write one sort function that works for all data containers that have defined the iterators, right? So this is a key concept in C++, like how to do generic stuff to make our life easier. There's also good reason of doing this. Once you improve the sort function, let's pretend that you make it as 10 times faster than before, then you make all the calls for this function for vector, map, list, my container, your container, 10 times faster for free without changing any line of code. So this is a really key concept in C++. Okay, so we have 15 minutes and then we will start a marathon on STL algorithms. So I picked 15 algorithms and we will go as fast as possible over all of them. So the STL algorithms are about 80 or even more standard algorithms. They are defined on the algorithm library on the header file. It's part of the core C++ library, so it's not a third-party library, so you already have this. They operate on sequences defined by a pair of iterators for inputs or single iterator for outputs, depending on what you want to do. And then the key message is don't reinvent the wheel. So before writing your own sort function, just go and check on the CPP reference if it's not there. So it's very unlikely that incredibly smart people from the C++ standard committee and the C++ community is not smarter than you, and then you will write a better sort function than these people. So basically, in this case, you need to trust these people and 40 years of C++ programming experience and say, okay, I will use a sort function provided by C++. Unless it doesn't work for you. So when using any container like vector, array, or maps, please don't write your own algorithms unless there is something that is not on the standard library. And let's pretend that you're not using STL containers for any given reason. Then just provide the implementations for the standard range access iterators, so begin, end, and all these kinds. You will have access to all these algorithms for free. So you don't need to rewrite a sort function, even if you have your own data container, like I know, my container or whatever, you name it. So if you provide iterators for accessing this container, then you already have for free all this functionality. So it's really important. And there's a lot of functions in SCD which are at least as fast as handwritten ones. So this is the selected ones. So we will go fast. There are like 100 of them, so I will not explain all of them, and they're like really flexible. Maybe the syntax might be ugly on the very first shot, but it's because it's meant to be flexible for any data type. First, sort function, really easy. We have a container that is this guy. We have some integer numbers, and then we want to sort this. How we do it? Calling std sort including the algorithm library. This is the typical syntax. So you will need to pass the first element of the container with an iterator and the last element of the iterator, and then you will sort your array. So if you inspect the output, so after sorting, you will have the sort function. Why there is no such thing as std sort and just use s, like sort this array? Again, this might be more ugly or much verbose syntax, but it's much more flexible. So for example, instead of doing begin at the beginning and then end, you can do the other way around and then you get the inverse sort, right? So this is why we use this syntax. Check this example at your computer. Number 2, fine. So we have a vector, for example, with 5 elements, and then we want to find if this element is on the vector. So we will call std_find, and then we will provide the beginning of the container and then the end iterator of the container, and then the element we want to check. And then this result will be actually an iterator. So if this iterator is different from the end, so let's do it with different colors. So if this is basically the same as doing this means that it contains the element because it searched through all the elements and it find it like at this point. And if it's equal to the end, this means that it went all through all the data and it didn't find it. Next, fill. Let's pretend that you want to fill this vector with a -1, then you just call std_fill, again, the beginning of the container, no matter the type and the end, and then the number you want to put, you want to use for fill. You try it, you will see this works, it's super fast. Count, for example, let's pretend that you want to count how many times the number 3 appears on this container. So we have it once here and once here. So we just call std_count, and then again the beginning of the iterator, the container, the end of the container, and then the number we want to count. In this case, n1 is 3, so 3 is 2 times, and then 5. If you search 5, it's not here 5. So whenever you count for 5 on the same container, you will get 0. Right? Because it's not there. As you see, like most of these examples are really easy. Ideally, you can try all these examples at your home. And there is some weird thing right now I will show you. I try to avoid the usage of lambda expressions on this, that this is actually how you will do it and how you must do it. But in order to keep stuff more simple for you, I just did some hacks on the code. So count if, let's say, okay, I want to count all the elements that are divisible by 3. So I provided a small utility function that will give me a Boolean variable and will tell me if this number I is divisible by 3. And then I want to count if these, like how many items on this array are divisible by 3. In this case, so how many we have? We have 1, that is 3, 2, 3, and 4, that is 9. So all these elements you can divide by 3. So the output should be divisible by 3, it's 4, right? So you can see that there is a pattern. So most of this stuff, if you actually need to do it handwritten, you will write for loops. And there's a much better way of doing this that is calling these standard algorithms. So instead of doing a for loop over all the items and say if this item is divisible by 3, then add a new element, increment the count, you just call this standard function and that's it. So there's a question that instead of begin and end, it's possible to only check a subset of the array and the container. That's actually a great question. I'm glad you asked. Depends on the algorithm. So I will show you now like how I check for algorithms, and then some algorithms provides like a way of using a subset of the array. But yeah, this is possible, of course. For each, I lost the count on the examples. So there's a small lambda expression here. So this is basically a function, so don't worry. It will print wherever you provide to it. And then let's say that we want to print all the numbers on this array, and instead of doing a for loop, we want to do a for each, right? This is an algorithm. Again, we provide the beginning of the container, the end of the iterator, and what we want to do. This is also called the predicate, right? So this is the function we want to do over all these elements. And then you will get the output, all the elements on the array, without writing any for loop. Super fast. All of. More examples. So in this case, we will have a vector with 10 elements that has 2. So if you print this vector, you have 2, 2, 2, 2, 2, 2, 2. And then in this case, we'll repopulate this vector with partial sum. So go and check it out the thing, but basically you're doing a sum. So if you, after this partial sum, you have the print, and then you see how you start adding the elements in increasing order. And this is the numbers we want to check. And then we will be using this all of algorithm. Again, the beginning, and the end. And then the predicate, in this case, it's the even function that will tell me with a Boolean variable if the number is even or not. In this case, if all are even, then we'll print all numbers are even. So among all these numbers, all numbers are even. There is no one single for loop. This is super fast, and besides the syntax of, if you're not used to see syntax with iterators, the intent of the code is really clear. I want to check if all the numbers are even. This is super fast. You don't need to write for loops. It's super cool. Use it. Rotate, for example. So this is a shift rotate operation. So we have this element, and then for example, we want to rotate this array. So let's use arrows. In this case, so this element right here will be the second element from the beginning of the container. So you can use this syntax with iterators. So this is basically pointing to this right place in here. And then you will rotate shift from this point. So if you see this, the output after the rotation, it will start from 3, 4, 5, blah, 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 and then 1, 2. And then if you try this at your place, you will see that the results are correct. I'm going super fast because the idea is to give you a quick overview on what you can do, and not to really explain like how this is implemented and blah, blah, blah. In this case, we have a transform algorithm to convert any string to an uppercase. So the syntax in this case is a bit more complicated, but again, the beginning and the end of the input array, and then we will create a second array that will be the output one, and then we only need the beginning of this array that is going to be populated with the output. And then the predicate for calling this transform function on each of these elements hello is uppercase. There is a function that will basically return the uppercase letter for this character. And then if you try this, it will convert hello from hello in capital letters. So again, no for loops, easy to use, hard to misuse. Accumulate. Again, let's pretend that we want to sum all over these elements. How you will do it? How I will do it? I will write a for loop and do for all elements in vector, then sum plus equal to blah, blah, blah. Just use accumulate. just keep the beginning of the I'm tired of saying this, but I will keep doing it. The end of the container, and then this is basically the offset. And then if you sum 1 plus 2 plus blah blah blah, you will get 5t5. Let's pretend that you actually want to use you want to calculate the product of all the elements. Then you do the same. This is the predicate, so std multiplies, and then with 1, if you do with 2, you will get 1 times 2 times 2 times 2 times 3 times 2. Just try it on your home and you will get the product of all the elements in the array really easily. Maximum, there's nothing to explain about this. Just calculate the maximum between two numbers. Minimum element. So with this you will get the minimum access to the minimum location of the element. Minimum min-max element. So you will get a pair of the minimum element and the maximum element. There are many of them. There is minimum, maximum, minimum element, max element. Just go and check it out on the CPP reference. Clamp. This is something new on C++ 17. And in my case, it's a function that I always tend to write for any given reason. Especially if you're writing like PID loops and then you want to do wind up operations. You always end up doing a clamp function and it's usually wrong. It's 2 lines of code, but it's much better to use the one provided in the C++ standard. So in this case, you will clamp the value between two minimum and maximum variables. So it's going to be in between 0 and 1. And then if you for example, query this with 0.5, then this is between the range. It's going to be fine. This exceeds the range max, so it's going to be truncated to 1, and then you see it here. This stays the same, and then this will be truncated to 0, and then you see it here. So use these algorithms. And lastly, sample. This is something that you might use on our field that we do a lot of probabilistic stuff. So let's quickly see this. So you have a string and that is C++. It's cool. I'm hoping to convince you. And then you have another string that will be out, and then you will create a random device using this random device. So it's defined on the random library, and then we want to randomly pick 5 letters from this string. Then we will sample again the beginning, the end of the string that is called in, that is C++ school, and then you need to use this syntax. Don't worry about it, but it's basically you're giving access to the back of the out variable that is a string, and then how many samples you want, and then the random device. And then if you see this particular example, it's probably different from the slides you have because it's completely random. So in this case, the 5 characters that pick is C++ and CL. So C is from cool and the L as well. So probably you have different output on your slide. Okay, so keep in mind, use STL algorithms. I hope I convince you that it's much better to use this type of generic programming techniques than just writing your own functions. Much more information on the C++ book, and also let's click quickly here. And let's see, for example, a lot of information. So if you go to the CPP reference, so here you have a list of all the available algorithms. For example, we saw transform. I think this is the uppercase example. And then the syntax is quite ugly, so I'm sorry. But actually, if you try to read this, whenever we see templates, it's going to be easier for you to read, but it's not that hard. So don't worry if you don't understand it right away. But these are all the function prototypes for the transform function. So if we do transform, you will see that there are many types of calling this function. This is the explanation on the arguments, and usually you have an example here that might be the same as I use or different on the slides. And one, for example, let's pretend that you only want to do uppercase of the first 2 letters. That I think this is also part of the question. So if the algorithm doesn't provide you with some sort of mechanism, one way of doing this is calling begin and then, for example, begin +2 instead of the end. And this is also one of the reasons you want to use iterators, because it will give you a lot of freedom on how to operate with your data. If you want from the beginning to the end, from the middle, so you lose all this capability whenever you just call sort and then you pass an array or a container, because then you are the only thing you can do is just sort this array. But maybe you just want to sort the first 10 elements, so you will use begin and then begin +10. I think this is a better answer for your question, the last question. Okay, that's it for now.